Our first speaker of the afternoon is Dr. Subodh Bapat from Sun Microsystems, and he's going to talk about future of data centers.
Thank you. Everybody hear me okay? Okay, good. I'm going to sort of up-level the conversation a little bit and talk about what's going on at the data center level and how that affects some of the research and some of the innovation that we're trying to drive down at the systems level, because increasingly the problem of designing computers, designing servers, designing networking switches, designing storage systems is not just a problem of designing the box. It is a problem of designing something that is a good citizen of a data center. Increasingly, servers and such are considered to be components. They're building blocks of a data center, not an end unto themselves. And so for that reason, what happens at the data center level is beginning to increasingly influence server design. And so just a brief history of what we mean by a data center. So what I did was I plotted the evolution of data centers in roughly 12-year timelines. And the reason I did that is because the average lifetime of a data center is about that much. People don't use a data center for 20 or 30 years. About 10 years is when it begins to run out of steam for various reasons. And in the 1970s, we mostly considered a data center to be kind of MIS glass house that had an IBM mainframe of some sort and card punches and so on. And that data center wasn't very big. It was maybe 500 square feet, and it didn't consume a lot of power. The instructive thing on this chart is the y-axis on either side. And if you look at the growth of data center space, floor space, as well as data center power consumption, you'll notice that the y-axis is actually exponential. It goes by, for this semi-log graph, so to speak. It grows by a factor of 10, both for power and for size with every generation of data centers. So in the 1980s, we had PCs and we had client-server computing and so on. And the client-server backend, we had, data centers grew to maybe about 5,000 square feet because we now had servers. And the power consumption grew to about maybe half a megawatt or so. Still not too bad. But then in the 1990s, with the first generation of the internet data center, we had an enormous explosion because the first generation of internet hosting providers, if you ask them what kind of data centers they were building back then, about 15 or so years ago, these are companies like Exodus and Digital Island and other names from the dot-com era, the dot-com boom era that no longer exist. But they were building data centers that had three-tier architectures, web servers, application servers, database servers. They had load balancers, they had switches, they had firewalls, and so on. And the size of the data center typically went to entire buildings. It was no longer a room in a building. It was a specialty building in and of itself. 50,000 square feet, about typical 2 megawatts, 5, 8, 10 megawatts. That was roughly the order of magnitude. If you look at the new generation of data centers that is being built today by the big giant internet service providers, by HPC, university labs, and so on and so forth, they are of the order of 50,000 square feet, roughly, anywhere from 30 to 80, 100,000 square feet. And 50 megawatts now is not uncommon. The largest data center that I know that's being built is by a hosting provider called Terramark in downtown Miami. And that data center is going to basically route all the internet traffic between North America and Latin America. Why? Because the undersea fiber optic cables, they all land in Miami. And that data center is 75,000 square feet. And they've put in a permission to Florida Power and Light to consume 80 megawatts. And so FBNL is actually building a special plant, power plant to service that data center. And so what happens is when you're growing the back-end computational capacity at that rate, you cannot just go ahead and do energy management and power and cooling management as an afterthought. In the old days, you would rent a room, you would fill it up with racks, and you would then figure out how much air conditioning you needed. Today, what you do is you say, what's my overall power envelope? How much power can I get into this? And then you design the data center. Then you figure out the computational capacity that you can accommodate within that envelope. And then, obviously, you want it as heavily optimized as you can possibly make it. And that means you're looking at all kinds of new features, airside economization, and I'll explain what all these things mean. You're looking at much more efficient server design. You're looking at putting in all kinds of intelligent firmware, not just inside the computer, not just inside the server or the storage device or the networking switch, but you're also looking at intelligent software that manages the whole building, that manages the air conditioners, the power distribution infrastructure, the UPS systems. There's a ton of supporting equipment, infrastructure equipment that exists in the data center that all needs to be optimized for efficient performance. You probably heard the statistic that for every watt of energy that is fed to a computer server, for the work that it does, and the work that it does might be credit card transaction validation, or it might be an HPC computation, or it might be servicing an HTTP packet, or it might be a search activity. But for every watt spent on that activity inside the computer, you spend probably anywhere from 1 to 2 additional watts in the air conditioning equipment to remove that 1 watt of heat that is produced by the server. And so that's kind of the equation that you're trying to optimize here. And there's a lot of, and I'll just throw some data at you. The number of data centers is actually growing. If you look at the people that analyze real estate trends on Wall Street, you will find that every real estate trend is actually going down. The amount of total million square feet under commercial real estate, under retail real estate, under residential real estate has been going down for the past year and a half. The only piece of the real estate market that has been going up and increasing steadily at a rate of about 4 to 5% per year is data center real estate. So
Are these numbers for the U.S. or worldwide?
These numbers are from IDC. I believe they are U.S. only at this point. Yeah, I think that's right. Yeah, that's right. And so we also did a projection of the number of servers in data centers. And this projection is from IDC estimates, and it takes into account things like virtualization, which actually cause server consolidation to happen. But even after that, it turns out that because of the explosion of things that people are doing on the network, and that includes not just social networking, but media downloads, MP3s, and photographs, and YouTube, and everything else. The total number of servers that is being deployed in data centers is growing and will grow from roughly 26 million this year to about 35 million in the next 3 years or so. And why is that? That doesn't necessarily mean that the server vendors are making a lot of money because each server gets cheaper over time, but that's kind of what's happening. But with increasing penetration and increasing energy consumption comes scrutiny. And there is a lot of activity going on right now in the regulatory bodies to regulate the power consumption of data centers. And that includes mandates, congressional mandates. The United States Environmental Protection Agency recently, as of last month, expanded its Energy Star program that governed primarily consumer appliances to cover computer equipment as well. And that includes servers. They have recently issued, just last week, they issued their first draft framework specification for Energy Star for storage. They intend also to expand the Energy Star program to entire data centers. And by that I mean that if you run your data center efficiently, you can get the whole building certified as Energy Star compliant. That's what's happening in similar regulations are happening in Japan and the European Union and several other locations worldwide. For enterprises, there is an economic imperative, obviously, to controlling energy costs, and it's not just because their data centers are getting bigger, their business apps are getting bigger, the number of servers that they're deploying are getting bigger, but the price they are paying per kilowatt hour is also going up. And so this is kind of compounding sort of the perfect storm. There's a number of trends that are sort of creating this perfect storm. One is, as I said, the increase in the unit volume of servers being deployed in data centers. each server, each generation of servers actually consumes more power than the generation it replaces. Why? Because the microprocessors got faster, there's more memory in the servers, there's more disk in the servers, the fans in the servers are more powerful, et cetera, et cetera. And so I did a trending analysis of that, and it turns out that the average power draw of, let's say, a 1 rack unit high, 2 processor server increases at the rate of 16% per year, and this has been a steady trend over the past 9 years or so. And then, of course, you add to that the price of electricity going up at 12%, 13% per year, and then you get, pretty much a roughly 50% year-over-year growth rate in the total cost of operating a data center. And that number, it could grow to as much as $200 billion worldwide. We find that the percentage of IT costs that is the power bill is actually going up. Every customer tells us that. Here's what happens. Here's why data centers are not designed efficiently. This is a typical layout. You put the data center in the middle of the room. Why? Because you have a building and you need a place to put the computers in, so you put the data center in the middle because you want to give the window offices to all the people, and so you put the server racks in there, and then of course the servers generate heat, and so along the edges of the data center you put some crack units, as computer room air conditioners, to cool the data center. And if you take an infrared camera picture of this thing from the top, where the red are the hot zones and the blue are the cold zones, you'll find that the servers, generally have an exhaust air temperature roughly around 95 degrees Fahrenheit or so. This varies obviously, but it's fairly typical 95. And then the cold aisle temperatures where you feed the cold air to the servers, they're roughly about 75 degrees or so. Right where that cold air comes out of the crack units emit cold air at maybe 65, 68 degrees Fahrenheit. And so, the data center as a whole is air conditioned. There's still a ton of inefficiency in there because you have hot aisles next to cold aisles next to hot aisles, and the air mixes, and there's all kinds of thermodynamic entropy created there. And so, it's not particularly efficient. There are solutions for that. But then if you look at the area outside the data center where the people are, you might find that the temperature there is maintained at 75 or 77, and the outside air temperature in a city like San Francisco or Berkeley might well be 55 degrees Fahrenheit. So what do you need to do? How much power do you need to supply to all of this? Well, in a typical building like this, you might have 6 megawatts of power going to the servers. And a typical ratio, what's called a PUE, a power use efficiency ratio, which calculates the fraction of power that comes into the building that reaches the servers. It's typically around 2 or so. And what that means is for every 1 watt of energy you spend on the servers for computational reasons, you spend another watt on air conditioning and other overhead. So it's not unusual to expect 6 megawatts of cooling power going to the air conditioning unit. And because the air conditioning is located right at the edges of the computer room, it makes these offices really, really cold. And so you need heating again. So you need 1 megawatt of building heat coming into this office. And by the way, this is sort of a generalization of a real example that we studied. And so you're heating all of these, and the outside air temperature is 55. If you found a way to get that 55-degree air somehow directly to the servers where the cooling is needed, then you'd save a lot of energy. So we're actually working on all kinds of improved designs, not just for designing the next generation box appropriately, but also the next generation rack and data center appropriately. We're using a technique called hot aisle containment, where you don't allow the hot exhaust air from the servers to mix with the cold air from the air conditioners. And so what you do is you enclose it, you create what's called a pod, and that becomes a building block, and that becomes a unit of scaling. Compute, power, cooling, and all of that across your entire data center. You can deploy these things on concrete slab floors. Increasingly, data centers are looking like they are industrialized operations. They're no longer office, commercial building type applications. They're more like factory floor style applications. And so you can deploy these things on concrete slab. You bring in power, you contain the hot air, and you run the hot air directly into the air conditioning. So you don't allow it to mix with the cold air. That gives you dramatic power savings. And so, we have all kinds of techniques to do hot aisle containment. The other thing that data centers are doing to increase efficiency is something called airside economization, and that's just a fancy name for opening the windows. And what airside economization is a city like San Francisco, where downtown San Francisco, you've got hundreds of data centers, literally. You've got banks, you've got airline data centers, you've got all kinds of things, and they're all enclosed, and they're all powered by air conditioners that chill them down and operate them at 68 degrees Fahrenheit. It doesn't matter what the outside air temperature is. The air conditioners are always going and keeping the data centers at 68 Fahrenheit. We did a calculation of the weather patterns in San Francisco. Turns out that roughly out of 8,700 hours in a year, more than 5,000 or so hours every single night and almost all through the winter, the outside air temperature in the city of San Francisco is less than 68 degrees Fahrenheit. And so if you could only bring in the outside air and use that to cool the data center, you wouldn't need to spend money on air conditioning. So people are beginning to do this. People are beginning now to locate their data centers. When the big search engine giants go out looking for data center space, they look for not just where it used to be 10 years ago, they looked for where the network bandwidth was the cheapest and most available, because network bandwidth was expensive and slow. What's happened over the last 10 years is that the price of transmitting a gigabit per second of network traffic has plummeted dramatically, because fiber optic cables have made network bandwidth extremely cheap. And so your data center could be located anywhere, because you can pump gigabits and terabits of data per second pretty much anywhere in the world right now. And so what's happened on the other hand is that the price of electricity has gone up. And for that reason, people are looking at where I can get power cheaply and plentifully, and also where I can get free air cooling cheaply and plentifully. And so the country of Iceland, until about a year ago, before they ran out of money, was advertising itself as a great place to locate data centers. Why? Because it's got carbon neutral or carbon free power sources through geothermal. It's got free air cooling because it's cold there all the time, and it's a great interim landing point for all the transatlantic fiber optic cables that cross the Atlantic. And so you put it there, and you have great traffic characteristics going to both Europe and North America. The other interesting thing people are doing is earth pipes. So this is an interesting technology in which it turns out that if you pump air at whatever temperature it happens to be, you pump it underground, roughly 30 to 50 feet underground, through a network of pipes for about a mile or so, it comes out at a nice even temperature of 65 degrees Fahrenheit. And this seems to be true pretty much everywhere in the world. And so the new data center construction, people are doing not just airside economization, they're putting earth pipes in there, and they're using that air, kind of free air cooling. And of course, we know of a company in Japan that is designing a data center underground in a disused, unused coal mine, again, because you get free air cooling. They're putting data centers in shipping containers, and they're sort of submerging them underground. And we know of another company that is putting data centers in containers and intending to locate them on decommissioned cargo vessels, so they can be docked outside of major metropolitan areas, downtowns where you do need data center space. And the advantage of putting a data center on a floating ship is that you now are sitting on the biggest heat sink in the world. And so there all kinds of interesting things happens. So it's kind of like that, yes. And you probably heard of there was a trade press article about Google applying for a patent that used a wave machine to generate electricity from the energy of waves that can then be used to feed a data center. So I don't know how serious they are about this technology, but there was that news article. So law of energy conservation is pretty simple. You have 50 megawatts of heat coming into the data center. That means you have 50 megajoules per second of heat that must be removed from the data center through convection, conduction, radiation. Why? Because there's no net accumulation of energy in the data center. Is at that level, it's very easy to understand. But there are all kinds of complications that happen. One of the complications that happens is that it costs money to remove the heat, and the price of electricity varies. Sometimes, obviously, it varies by geography, but sometimes within a geography, it also varies by time of day. You get cheaper power at night from many utilities. You get more expensive power during the day. So we have data centers that are using the price shifting capability. So, my friend Mark Bramford, who runs the data center program at PG&E, he says, to me, a data center is nothing but a giant resistor in a multi-megawatt circuit. Why? Because I give you 50 megawatts of power, and it turns it into 50 megajoules per second of heat. It would be nice if you were to take advantage of my price differentials and also make it look like a capacitor. And so what some data centers are beginning to do is they siphon off the cheaper megawatts at night, and they create a form of stored energy. It's very expensive to store energy. You can't do it in batteries because it's very capital intensive. What these people are doing, they're freezing water using cheap electricity. And then during the daytime, they don't actually power up the air conditioners. All they do is convect air over the ice blocks, and then they get cold air that then they pump into the data center. So they save money that way. And so if you work out the thermodynamic equations and the spreadsheets for the cost value, it turns out that this actually works. There are other applications that cities and other companies are doing for reuse of waste heat. So you're shifting the energy cost not just in time, but you can also shift it in space. And how can you do that? Well, it turns out that the exhaust heat that comes out of a data center is pretty low-grade heat. It's water that comes out of the chillers that service the air conditioner at maybe 98 Fahrenheit, 100 degrees Fahrenheit. It's not hot enough to boil water or drive a steam turbine or regenerate the electricity through any kind of cogeneration activity. But you can find applications downstream, other applications that could make use of the warm water. So we have a customer that is a municipality in the city of, I can't name the city, but it's in the state of Indiana. And they used to have their own municipal data center where they had waste hot water at 98 Fahrenheit that they fed to a chiller plant into which they pumped in 2 megawatts of energy, and they got the cold water back to feed into the air conditioners for the data center. Separately, they also had a sewage treatment plant, which it required algae. It treated sewage through bacterial breakdown, and that needed water at 98 degrees Fahrenheit. And so they used to have 2 megawatts of heat coming into a water heater to feed the sewage treatment plant until some facilities guy in the city, had a brainwave, and they just used the warm data center exhaust water to feed the algae in the sewage treatment plant, thereby saving the 2 megawatts of electricity. When I was a doctorate student many years ago, my thesis advisor had this phrase, which was garbage in, garbage out, for running software programs. And so this is kind of an application of that. Hospitals have big data centers, but hospitals also do a lot of laundry. Laundry needs warm water. And so hospitals are trying to recirculate the warm water out of the data center as a downstream application. People are using it in municipal swimming pools, and so on. So I'll sort of conclude with three sort of high-level principles here, which is where the interesting research problems lie. There's a lot of innovation possible. It's not just innovation in electrical engineering. It's not just innovation in logic design, circuit design. It's not just innovation in software and firmware and intelligent algorithms. It's also innovation in thermodynamics. It's innovation in computational fluid dynamics. There's all kinds of things that we should be doing to make computing in general more efficient. It's not just a problem for a soda hall. It's really the whole university here. And I'll explain what these principles are. So the principle of totality means that every component for energy saving, for doing compute efficiently, every component, whether it's a component that goes inside the box or whether it's a component that's a component of a data center, needs to be involved in delivering energy efficient operation. So we don't just need to research frequency scaling and voltage scaling and core scaling at the microprocessor level. We also need to research how do I turn off chunks of memory in the server, and how do I change the operating system so that when the operating system schedules threads or schedules jobs on the available microprocessors or decides to do page allocation onto banks of memory, how does the operating system decide how to pool these things together so you only turn on the minimum compute infrastructure that you need to and don't turn on any more than you absolutely need to? How do you design algorithms for that? And so it's not just inside the box, but it's also how do I make the power supplies more efficient? How do I make the efficiency curve of a power supply distribution mechanism? Because remember what a power supply does. It takes in 110 volts from the supply side, and it delivers maybe 5 volts or 2 volts or 1 volt to the motherboard of a server. And the power supplies typically are only in the range of 70 to 80% efficient. So if a server burns 2 kilowatts, it's quite likely that if you're not using a top-of-the-line power supply, you're losing 600 watts in just the power supply. So that's a lot of energy to lose if you have 10,000 servers in your data center. Same problem that applies to power supplies also applies to UPSs, the uninterruptible power sources that sit at the back of a data center. Air conditioning, chiller plants, all need to be involved. So my ideal vision is that the data center, there's an intelligent console, the God console, if you will, that understands everything that's going on in the data center. It understands where the virtual machines are running. It understands what the utilization level is of every single server in the data center. Every network switch, it knows how much traffic is coming in. It knows how many gigabytes per second of I/O operations are going to the disk drives. But it also knows temperature information. It knows the temperature profiles. It knows the electricity prices of the pricing of each incremental kilowatt hour that you get from the utility. And it has this giant optimization algorithm running somewhere that's optimizing which servers are on, which ones are off, which ones are frequency scaled up, which ones are voltage scaled down, which VMs are migratable from one machine to another in order to run the data center at the most efficient, in the most efficient manner possible. And so that's the principle of totality. Everything needs to be involved. The second is what I call the principle of agility, which is the data center needs to be responsive. It needs to be responsive to changes in network traffic and offered workload. If it's getting 10 gigabits per second of HTTP traffic during the daytime, it maybe 80% of its capacity needs to be on. But if it's only getting 1 gigabit per second of HTTP traffic at nighttime, maybe only 8% of its capacity needs to be on. So it needs to be responsive to power supply situations. The utility might tell you to brown out. It's browning out, it's losing power, whatever. You need to respond and calibrate your power consumption to that. And then the final principle is the principle of proportionality. And that, by that I mean, the real holy grail of where we're getting to here is this notion of energy proportional computing. If there's one phrase you take away from my talk, keep this in your head. It's energy proportional computing. How do I make sure that not just at the server level or at the network level or the storage level, that I am calibrating my power draw to match the workload that is being demanded of me. In other words, I shouldn't just deliver scaling in terms when my workload goes up and down. I should scale my energy consumption up and down, but I should also look at that whole problem at the data center level. If I were a big giant search engine operator, I would ask questions like, how many buildings do I have in which I run my search site, and what is the ratio? How many trillion searches do I do per megawatt of energy that I pump into each building? And because that lets me factor in all the overhead, the air conditioning and everything else into my calculations for energy efficiency of compute devices. So I'll stop here, and I think we've got a few minutes for questions. Okay.
Great. Any questions or comments? Hey, Mike?
We've heard this point a couple of times about the importance of optimizing the total system, right, and not just one of the subcomponents. But as I hear this said by a couple of speakers, I'm wondering who's responsible for bearing the cost of doing that, because optimizing the whole system is, of course, more expensive at the outset. You may save money, but it's a lot more expensive at the outset than just optimizing the subcomponents. So who's responsible for bearing the cost of that total optimization?
So ultimately, the customers that run data centers end up paying the power bill. That you're asking, you sort of, if I finesse your question just a little bit, within most organizations, there is pressure on the vendors of compute infrastructure equipment, server, storage, and network vendors, to be energy efficient, but there's not as much pressure as there should be if, in fact, the people that ran compute for the organization, whether it's a university or a corporation or whatever, were also responsible for the power bill. And in fact, that is not the case. In more than half of the customers that we have studied, the power bill does not go to the CIO. The power bill goes to the VP of real estate, and it's bundled in with the power bill of all the other buildings as well, not just the data center. And so that trend is changing. About 5 years or so ago, only about 10% of CIOs were responsible for paying the data center power bill. Today, it's up to about 45%. So that's good, because that then makes the CIO responsible for data center energy, and then they can put more pressure on their vendors like us to make the equipment more energy efficient. So.
Good point. Okay. All right, Ivan, last question.
So it seems to be a trend to make the data centers bigger and bigger, but this creates a single point of failure for critical things like computing as well as network interfaces. So is there some optimum size that you can think of, or ways to back these things up?
Yeah, so there's redundancy and resiliency for all your mission critical applications is done at many levels. So within a single data center. So first of all, we build in redundancy within a server. So when we ship a server, we don't just ship it with one power supply or one disk or one fan, because these components fail from time to time. We have redundant fans and redundant cooling, redundant power supplies, etc. So we do that just within the box. Then at the solution level, within one data center, but across a few racks, you might build in redundancy there. And so you might have two different servers in an HA configuration, where if one fails, the other's a hot standby, and takes over the operation of the failed server if necessary. That is wasteful of energy, but for mission critical applications you need it. Then of course there's geographic redundancy. So redundancy, which is I think the question you're asking, redundancy across multiple sites. If you have a whole data center that goes out due to an earthquake or a natural disaster or whatever, is there some other place that can take over the load? And some of the bigger, really big mission critical operations, the credit card companies, the financial companies, the big ISPs, etc., they do have some solutions that involve global load balancing and so on and so forth, where you can redirect traffic at relatively short notice from one entire data center to another across geographical boundaries. So there are solutions for handling that.